Good afternoon, everybody. Can I have your attention, please? Welcome to our bi-weekly Csaaw seminar. And today we are honored to host our professor, Jing. She's from the Academy of Mathematics and System Science from the Chinese Academy of Science. She's a tenured professor there at very relatively young age, as you can tell. And she also, her interest is cover complex adaptive system, collective behavior, intervention of multiple agent systems, and optimization problems. And today she's gonna share with us one of her research on intervention in multi-agent systems and games. So please give a big applause to our guest today.
So can you hear me?
Yes.
First of all, I want to thanks to the organizer of Csaaw to give me such a great opportunity to present my research here. And I'm very greedy that I want to talk two different topics in this talk. And so I noticed John told me these two colors are the colors of University of Michigan. Yeah. And so the first topic is about multi-agent system, and I will talk about the intervention on collective behavior of multi-agent systems. The other one is about combinatory game. So the first part, the title of the first part is soft control on multi-agent system. So now we start with the conclusion. And the question here is, given the multi-agent system, if it's not allowed to change the interacting rule of agents that are already there, then is it possible to control the collective behavior of the multi-agent system, and how? So in this talk, my answer is yes, it is possible by adding one or a few shells, which is special agents. And I will talk about this by two case studies. One is based on a floating model. The other is based on a multi-person game model. And I call this method soft control. Okay, now I will tell you the story about that. I think many of you know that for a system with many agents, or we call it individual or class, they locally interact, and we will see new properties emerge, like phase transition, pattern formation, group movement, swarm intelligence, and so on. And I would like to classify research on collective behavior into three categories. The first one is analysis, that is, given the local rule of agents, what is the collective behavior of the system in the microscopic level? And the second one is design. That's given the desired collective behavior on the top level, what is the local rule for agents in the bottom level? And the third one is called intervention, that is, given the local rule of the agents and how we intervene into the system and to get the desired collective behavior. So I will develop a concept called soft control, and this is what this talk about. And by presenting the idea, I will give you two case studies. The first one is based on a floating model, and I will try to use a shield, an intelligent shield, to lead the group to reach consensus. First is the model. I don't know how many of you have heard about this model called the Vixen model. Yeah, and in this model, it has n agents. For each agent, we define a neighborhood of an agent, which is a circle with radius of r. Then agents can feel and see other agents inside this area. So for every time step, if we're trying to adjust this ending, that is towards the ending, average ending of its neighbors. So this model is very simple, and every agent only knows the local information, and so they interact with the local rule. But we will see, this is a simulation of this model. And this little dots represent the agent here, and the red line represents its moving direction. And you will see floating behavior in this model. So the question here is, from some configuration, initial configuration, the system do not reach consensus. They will separate into several subgroups. But starting from some configuration, the group will synchronize to the same direction. So there are many, recently there are many scientists working on this self-organized behavior. Oh, you have a
quick question. What was the circle? Is that the size of the neighborhood?
Oh, the circle is actually the initial area that I distribute the agent in. So I will randomly distribute like 100 agents inside this circle. And that's all. And the neighborhood circle will be much smaller than that. I will show you a little bit. Yeah. Okay. So there are many analytical results about under what condition the group will reach consensus. But so far, there's still no sufficient and necessary condition. Okay, but what if the pool does not reach consensus? Can we intervene in the system and help without destroying the local rule of the already existing agents? Then we proposed the concept called soft control from 2005 with my colleague. And I will first talk about the key point of soft control. That is especially for a system with many agents, and each agent will move following the local rule, so the agents are autonomous and they are distributed. And agents will locally interact with each other, but they're not isolated all the time, so that the local effect might spread and affect the whole group. And the control here is that it is not allowed to change the local rule of the already existing agent. And there is no global parameter to adjust to change the collective behavior either. So one possible way is to add one or a few agents into the group, and that will not increase the computational complexity of the system, but it might not affect the collective behavior either. But what if I add special agent in it? I call it shield. So shield is like adding one shield is like adding a control interface into the system. So the shield is controlled by me, by us. It does not follow the local rule, but it is still treated as an ordinary agent by the ordinary ones. So a shield is not treated as a special leader. And this is why I call this non-destructive intervention, because the normal agent do not need to change their local rule to put more attention on the leader. So the strength of the shield, of its influence on others, is the same as normal agents. So normal agents do not avail the control here. So that's what I call soft control. Okay.
Professor,
yeah.
Just to make it clear, so every other agent, they have the same local rules?
Yes.
Except for the shield may have some...
Yes, the shield is controlled, can be decided by us.
Yeah. Okay.
Yes, yes. But the normal agents still treat the shield as a normal one.
Okay.
So, yeah. Okay, now I will show you a computer simulation just for the idea. And now I put 100 agents randomly distributed in this circle, and I will run. Now there's no intervention. It's a self-organized behavior, and it does not synchronize. Now, the same group, and I add one shield. And now this is like a computer game, and now in this video, I use my hand the mouse to control the position of the shield, and use the keyboard to control the direction of the shield. So this is just like a computer game. Okay, so you will see that I can use the shield to group the group together, and I can make it turn around, and I can even seduce some some agents from the group. So you can do a lot of things by adding a shield. So now I make it turn. It is just like a game.
It's like you're hurting.
Yeah, so if you have good skill, okay.
How many shields in this case? How many shields?
Only one.
Only one.
Yes. Okay, but this is just a game, and we need more serious. Okay, yeah.
Why does the shield have such a large effect? It's just 1 out of 10 agents.
You mean the effect of the shield?
Yeah,
It's
effect would be very strong.
it's not strong actually. It has the same strength. The influence of the shield has the same strength as the normal agents. It's actually the same.
Okay.
Yeah, but it's just so.
Average over many cycles.
Yeah, so for if a shield is in a normal agent inside the normal agent's neighborhood, when the normal agent decides its next step handing, it just calculates the average handing of all its neighbors. So if I put a shield inside its neighborhood, it will also consider the handing of the shield. But it's the same strength, not special. I mean, this agent treated just as a normal one, but it will have this kind of effect. Yeah.
You have some study. I'm sure you're probably going to present, but like how their influence of the shield can spread along within the flocks. Like maybe how the action of the shield actually eventually adopted by other agents in the flock. Maybe you're gonna show it later.
Yeah, I will show later. Yeah. So I need a more serious study of this case. Now I consider a system with n agents that with initial handings belong to 0 and to pi, and I add one shield in, and the goal is to lead all the agents move to the direction of 0. This is 0. So to do this is the 0 direction. So the problem is what is the moving strategy of the shield to accomplish this task? First, I want to talk about the attributes of the shield. I think this shield is smart, it's intelligent, because it can use feedback information of the group, and it might know more information than other normal agents. It does not follow the alignment rule. Indeed, it can be redesigned, and it has its own strategy. That is, it will try to affect the bad guys. Bad guys means that the agents that are not moving to our desired direction, that's the handing 0. And it will need more energy because it has to move faster than normal agent. Otherwise, if an agent moving away, it will have no chance to catch up with that one. So it should be faster, but we can prove we do not need unlimited speed for the shield. So it has a bound to accomplish the task. So to affect a bad guy is actually to be close to the bad guy and inside the neighborhood, and so it will turn the bad guy to the handing within a few steps. So this is easy, but how to make handings of all agents converge to 0, and that's much more tricky. So there are two key points for the strategy of the shield. First one is we know from some theoretical study that is called the joining connectivity theorem. That tells if the shield can theoretically affect every agent with handing 0, then the group will converge to handing 0. But the difficulty here is how after the shield affects a target agent, how does the shield move to the next target agent without putting negative effect? So I will show you that. For example, after the shield affect this guy, it trying to move to affect the next target. But if it move in this way, it will put negative effect on these two agents. So this is not good. And the simple idea to solve this is to move forward and make a big U-turn outside the group and hit the target agent from the left side. But this is not efficient either. and we need to find shortcuts inside the group, so it can be much more efficient. So the second key point is, if they are neighbors of the shield, then the shield should move with heading 0. But if there's no neighbor, the shield can move to any direction. Okay, so this is the strategy, the algorithm of the shield, which is designed with a finite state machine, and I'm not going to the detail because it's very complicated. And now I will show you that by using this strategy, now you see this blue guy is the shield, and the circle means the neighborhood, the size of the neighborhood. And it's the same. I mean, every agent has the same size of neighborhood. And now it leads all the guys move to the desired direction. This is a loose group, and we can consider a more crowded group. Oh, and if you can see that there's a green line between some agents, that means if they are neighbors of each other, they will be linked by a green line. But it will change if the distance is farther than r, then it will change.
Is there a minimum number of agents that interacted with the shield that can lead to their
No minimum.
No minimum.
Yeah, any size. So, but it just need more time.
No.
If the group is larger, then you need more time to make the group converge to 0.
Yeah, I mean here that you seem like the shield actually interacting with all the particles, all the agents in the group.
Theoretically,
Yeah,
yes.
theoretically, but is it possible that you just interact with a portion of the number of agents?
Yeah. Actually, it can if the agent is affected indirectly by the shield, that's okay. That's also considered to be affected.
Yeah.
So that depends on the interacting graph. So if a shield interact with one agent, and this agent is an neighborhood of another agent, then we can consider this agent is affected by the shield. So it's not necessary for the shield to directly affect everyone. Mm-hmm. Yeah. Okay. So and if the shield can move faster, then it can accomplish the task faster too. So now it's moving around inside the group and without putting any negative effect. Okay. So we have a theorem to prove that this algorithm will work and will lead the system converge. And with this strategy, the group can reach consensus, and the shield speed has a bound. So it does not need an unlimited speed to accomplish this task. And in practice, for simulations, we know that the shield can use a speed which is much lower than the theoretical bound to achieve the goal. So one shield can lead the group to consensus, and higher speed of the shield usually will lead to faster convergence. But if the shield speed is low, then low density group will need longer time. But if the shield speed is high, then larger group will need longer time. So, and we also compare this method with the method of adding a number of leaders, which is if you hear, I think maybe some of you know Carson's work, that they put some informed agent into the group, but informed agent actually is the agent that with fixed handing. So one fixed handing shield is like a fixed handing shield, but one fixed handing shield is not necessary. It's not enough. So they put a number of it, and we compare with this method, and we found that one intelligent shield will perform better than adding a number of fixed handing shield when it is measured by the synchronization level. So, and also more robustness in the case with noise too. And of course, following this slide, we will ask more questions, like what is the optimal strategy for the shield, and what if the shield can only see locally, and how much information we need to know about the system, and so on and so on. There are lots of questions we can ask. And I think soft control is not just for the weak set model, and it could apply to other systems. So the second case study is based on a multi-person game system, and we will introduce adding many shields to promote cooperation. So I think you all know the evolutionary multiplayer repeated prisoner dynamic game system, and cooperation might not emerge in this system. So soft control here is to add a shield to promote cooperation. We can see cooperation exists anytime, anywhere, from animal groups to human society. And we also see defection in a group of self-interest agents. So the question is, does cooperation exist in a group of self-interest agents? If not, can soft control introduce cooperation? So the model we study is the evolutionary multiplayer repeated prison dilemma. And I think many of you know this game, right? Prisoner dilemma. So it's a game that shows if two players both cooperate, they both win, they both get a good score. But if any of one change to be defeated, it can earn more, and the other will lose more. So if both of them think in the same way, they will both lose. So this game shows why two individuals might not cooperate, even if it's better to do that. And for a group of people that playing prisoner dilemma games, we found that cooperation level is very low under some circumstances. So Professor Exlord asked the question is, in what condition can cooperation occur from self-interest individual without centralized control? And there are many words studied on this question, like to find good strategy of agents, assign agent with extra ability, or locate agent on a spatial structure. And they are about how to decide the system. But what if the system is already there, is given, and it shows no cooperation? What can we do here? And our work is to promote cooperation in a non-cooperative group while keeping the already existing agent unchanged. They still do what they usually do. They do not evade control. Okay, so the basic model here is to consider NA normal agents. Their strategy is represented by the reactive strategy with YPQ. Y is the probability of cooperation on the first move, and P is the conditional probability of taking cooperation if the opponent's last move is defection. And Q is the probability of taking cooperation if the opponent's last move is a cooperation. So during every generation, we will pick up pairs of agents, and they will play an n unknown beta round prisoner dilemma game, and then we will update the fitness of two agents. And then after each generation, it will be a reproduction, and following the rule of survival of the fittest. And we found that from simulation that the cooperation level is very low in this model. So the frequency of cooperation will reach to 10% of the group. And this is the theoretical study for this self-organized behavior. Also proof that the frequency of cooperation will convert to zero if the interaction is complete. So our work is to put a few number of shields into the group and to increase the cooperation level. So we put NS number of shields, and the shields are treated as normal agent by normal ones, and they have no preliminary knowledge of normal agents strategy, but they can recognize other shields, and they will share information. So their strategy is frequency-based tit for tat. So they will cooperate with the player that has a higher frequency of cooperation. So they will reward cooperator and punish defector. So with more shields, so this is the red line has no shields, so the cooperation level is low. If we add more shields, it will increase, and more shields is increased again. So we see that soft control is possible to promote cooperation.
So what is a fraction of shields?
What
is a fraction?
Oh, what's the fractions? Okay. So this is for the complete interaction case. That means every two agents will play the game, and this is for the incomplete interaction case. That is only a portion of not everyone will play with each other. So for the complete case, that the group have 500 agents. And now the green line is 150 shields, and the blue line is 450. So it's quite a lot of shields. But in the incomplete case, this is the number of shields. So it's 30 shields, 60, 90, 120, and 150. So here we need much less shields to increase the cooperation level. And we also test the robustness of whether it's robustness to noise, and we found that sharing information is more important in short-term game comparing to the long-term game, and also in the case of partial share, that the shield do not need to share all the information with others, and partial share is also effective. And it also works in the case with mutation too. So, and this is the analytical result of this. And so from this case study, we know that soft control is possible to promote cooperation while keeping local rule in the original group. And its robustness to noise, mutation, and sharing information is important. And partial share is effective enough here. Okay, so soft control is for multi-agent system, and the goal is to change the collective behavior. But we cannot, while we cannot adjust global parameters, and we cannot change the local rule of the existing agents. But what we can do is to add one or a few shields. And the approach shows that one or a few smart shields can change the collective behavior of the group without changing the already existing agents. But there still need a lot more study following this line. We would like to see how to use soft control to intervene in other multi-agent systems, and how to use soft control to help design man-made systems, and also the controllability approach of soft control in a general framework, and also the anti-soft control problem, and so on. Okay, so this is all for the first topic. And I will go to the second one. And this one is about game, combinatory games. So, how many of you know 5 in a row? Oh, so, and I will show you a bit later if you do not know. And then I found there is a phenomenon called knowing more is less. I call it knowing more is less. That means if I know more about my opponent's strategy, sometimes I will lose more. But this only happens for bounded rational players. The motivation to work on this project is to look for new laws of cooperation or co-adaptation among agents. John is here, and John proposed the idea of complex adaptive system. and that is a multi-agent system, and agents there will adapt to each other through interaction. This is different than a single agent adaptation, that if an agent adapts to the environment or a static objective, the process is just like an optimization process. But if two agents adapt to each other, we will sometimes see very interesting phenomenon. That is to say, why the price climbs a post, the devil climbs 10. So if I can see this in my program, I will be very happy. And I think game is a typical example for co-adaptation and co-evolution, because players they interact with each other, and they are selfish. They try to maximize their own profit, and the opponent cannot be treated as a static objective, because your opponent is also adapting to you. So the case study here is 5 in a row, and I can show you a bit. So the game is playing on a 15 by 15 wall, and just like Go, and 2 players, white and black. And if a player can make the pieces of her color 5 connected, then he wins. So what I want to do is do, I'm going to lose. No, but it knows it has chance, so it's not in a hurry. Okay, so now the black win here. Okay, so this game is, the rule is simple, but the strategy is very complicated. If you want to be a good player, it's not easy. And if you write a program to play this game, the computational complexity is extremely high. It's p-space complete, which is higher or at least equal to NP complete. So there's no explicit solution. And it's impossible, at least now, for complete search for the whole space. So in this case, you have to adapt if you want to play better. So if you're going to write a computer program, the question you're going to answer is, for any configurations, what are my good moves for my next step? So to find a good move, usually I will consider all the possibilities. I will list all my choices, and then all my opponent's choices, and then all my choices, all my opponent's choices. So for example, if I face this wall, and now it's turn for the black to move, if we consider this place, this position, this and that, and these are all the possible positions for his next move. For each of my move, I will consider my opponent's reaction. So this is all her reaction. Okay, and for each of my opponent's reaction, I also need to consider all my reaction for the next step. So on and on until I found somebody win, and then this branch can stop here. But you still need to search the other branches. So this is called the game tree search. So this node represents the situation that the black player face, and then these are all the choices for the black player for the next step, and then this is the choices for the white player according to this, and then the black player and the white player. So again and again. So it's a huge tree. So if somebody win here, that I would like to use 1 to denote that B win the game, and -1 to denote white player win the game. So I will backward this number, because this is for this node, it is the choice for the white player, and the white player will like -1. So it's a minimized here, and then for the upper level, the black player will like 1. So it's a maximum. So it's maximum, minimum, and maximum. So it's a minimax, and recursive. So this is the algorithm for five in a row, and for most combinatorial game. Unfortunately, the tree is so big, it's huge, so there's no way to search to the end. So we have to stop when we reach some level. But then, because this is not an end game, and we don't know who is going to win from this configuration. In this case, we have to construct an evaluation function to estimate how good the current configuration is. And then, by doing that, we can still use the minimax process and to help the player to find the next move. But so the evaluation function here is the most important part for the strategy because it reflects the style of the player, whether it's aggressive or conservative, and it reflects how the player predict or judge the future, and it decides the dynamics too. But I think it's impossible to construct a perfect evaluation function that tells you whether you're going to win or not. So this brings out the concept of boundary rationality. Actually, this is a concept proposed by Simon Herb. That is to say, he said that individual decision making is always not optimal, limited by information that he has and the cognitive ability, and here is the computational ability of the computer, and time, and etc. Okay, so one way to construct an evaluation function for 5 in a row is to calculate the number of patterns. So the patterns of 2 in a row, 3 in a row, 4 in a row, and 5 in a row. And then we can construct an evaluation function as a weighted sum of the number of patterns. So for example, this is an evaluation function that consider 2, 3, 5, 4, 5 in a row, and for the white player, and this is for the black player with a weighted value. Okay. So this is all about the basic knowledge of 5 in a row. And now the overall framework of our approach is an evaluation function-based coadaptation. And I divided into 2 steps. For the first step, I want to see how players X adapt to player Y. And the next step is how they adapt to each other. And for the first step, I want to know what is good if X knows Y's evaluation function or its next move. So with more information, can a player play better? And how do players use information? And that is the question I want to answer here. Okay. And to answer the question, we do the computer simulation on 5 in a row. And we consider 2 players, X and Y. And we consider 2 evaluation functions. The first one, it's relatively good because it considers 2 in a row, 3 in a row, 4 in a row, and 5 in a row. For the second one, I think it's a relatively bad evaluation function because it does not consider 4 in a row. 4 in a row. It still considers 2 in a row, 3 in a row, and 5 in a row. So you might not stop the leaf 3 connected. But I should tell you that even with this bad evaluation function, the program is still not a silly player. It still plays okay, at least not worse than me. Okay, so I want to consider I want to make the simulation in different scenarios. So I will consider the case of X and Y don't know each other's evaluation function, and versus X knows Y's evaluation function. X move first versus Y move first. X with a good evaluation function and Y with a bad evaluation function versus bad X and good Y. Okay, so we have a combination for the scenarios. Now we need to fill this table. So this is the text set that is we will play the game from initial configuration that is 6 piece and 4 piece. So it's 2,000 random 6 piece, 3,000 random 4 piece. Okay, so for good X versus bad y, we will see that this is the percentage of x wins the game. So we can see if x knows y's evaluation function, the percentage increase slightly, like from 92 to 95, 49 to 50, 53, and a similar case here. So this tells that if x has a good evaluation function and y has a bad evaluation function, no matter whether x moves first or not, x will place better than when x knows y. So this fits our intuition, okay? Then we will ask, what if x has a bad evaluation function and y has a good evaluation function? Will x still place better? And what I found from the simulation is x plays much worse when x knows y. So this is a surprise. We see this table. So you see the percentage of x wins the game, that if we do not know y, it's 77, and we decrease to 37, and 31 decreased to 2.3, and a similar case here. So this is really strange. And that means that if you know more, you lose more. So knowing more is less here. Why? So for the first time I saw this result, I think it must be bugs in the program. And then the second question is it a general phenomenon in combinatory game or just in F5 in a row? So to answer this question, I think it's too complicated to analyze the program of 5 in a row, and it might not be extended to other games. So what I did is to build a theoretical game model, which is simplified so we can do maps on it, and still keep the extents, and still show the phenomenon. And it's more general, so it can be used to explain other games. But I'm not going into the detail of the theoretical model, and I will just give you some feeling. So this is, I call this an H-game game tree, and it's artificial. And one thing very important is I construct a measure called accuracy rate, which is C here. That is a rough measure for the performance of the evaluation function. So accuracy rate C is the probability of the evaluation function that can give the same evaluation value as the standard minimax process. So if C equal to 1, that means the evaluation function is a perfect evaluation function. It can have the same effect as the standard minimax process. Okay. So does this model still show the phenomenon? Yes. So when X is a bad player, for example, the accuracy rate is 20%, is 0.2. Then we can find the number of X winning the game is decreased sharply comparing to X knows Y. So it still shows the phenomenon. And based on this model, we can do some theoretical, mathematical analysis here. And this game playing process can be written as a Markov chain. And so this is the numerical result of this Markov chain. And we found this is the accuracy rate for player X, and this is the winning probability of X. And the blue line is the winning probability of X when X knows Y's next move. And the green line is X and Y don't know each other. So you will see that when the accuracy rate of player X is larger than 50%, then having more information of your opponent will increase your winning probability. But otherwise, it will decrease. So the same thing happens here for another Y. So the reason behind this phenomenon is it's a bit complicated. But what I can tell you here is, I can give you not very precise but very intuitive explanation is that low-level player is not good at using information. So with more information, it will make worse decision. And knowing more, the phenomenon of knowing more is less only happens for boundary rational players. So if it's a rational, if it's a perfect player, then knowing more is more. That's always true. So this phenomenon does happen. So knowing your opponent is not enough, and you still have to improve your own evaluation function. And I think this phenomenon is a special phenomenon in co-adaptation, co-evolution. And information plays a very important role in co-evolution. So I think I will continue the study following this line. And what I'm most interested in is to see co-adaptation or evaluation function in combinatory game. So I think games are a good example to study co-adaptation and co-evolution. I think this finding is just the tip of the iceberg. And I hope at the end we can answer the question of how adaptation builds our complex world. Yes, and that's all for my talk. And if you're interested, you can download the demo talks and papers from my website. And this is the building of my office in Beijing. So if any of you visit Beijing, and you can email me, and I will be happy to show you around and even give lectures there. Yes. That's all. Thanks.
Could you go back to where we can download your papers? Thank you.
Oh, okay.
Just wanted to copy those.
Any questions?
Yeah.
So in your presentations, so X knows the next step of the Y, which means even X knows the next step of the Y.
Yeah.
X can be tricked by the Y, right? So
No, you mean Y will fool X?
so Y, yeah, Y. So that is why the evolution function of the evaluation function of the X is not good enough,
Oh yeah, yeah.
right?
Yeah, so if X knows Y's next step, that means when I consider the game tree, I don't need to do minimize, because I already know what is Y's choice in the game tree.
So
If I do not know it, I have to do maximize on the game tree.
okay, so only consider one step instead of multi-stage.
Yeah, so now I only consider max. Yeah, because I already know what is your choice. So we do not need to minimize here. So that means if I'm thinking about how to, where to put my next piece, I think if I put it here, I will know what is your reaction to my move. I know that. So, and then I will think, oh, maybe I put it here. And then I know if I put it here, you will put it here. So that's what I know. That's it. That is what I mean. X knows Y's evaluation function, or X knows Y's next move.
Okay,
Yeah.
which means that there is no minimization with evaluation.
Yeah, in the game
evaluation
tree.
function.
In the game tree, yeah. In the game tree, yeah. In the game tree search, yeah. Yes.
Does it matter how accurate Y is, or is it just a matter of whether X is better or worse than guessing?
Yeah, actually, no, it doesn't matter for what Y is. So whether Y is good or not, it does not matter. So only matters is how good is X. Yeah.
It's very similar to dogs with.
Oh, sheepdog. Yeah, people mentioned that to me too. But yeah, it's similar, but it's still a bit different because for sheepdog, the sheep knows that is the dog, so the sheep feels scared to the dog. But here, the normal agent do not know this is a shield. They just treat it as a normal agent. Yeah. Yeah, but they have some similarities there. Yeah.
Do you have any other questions? All right, so thank you, Professor Han, once again.